Welcome. My lecture is on the physics of depletion region of PN Junction semiconductor devices. Now, why the depletion zone is so important? We observe that based on different electrostatic properties of this zone, we achieve the present day unbelievable electronic industrial developments and applications. The most important uses of PN junction properties are in rectifiers, stabilizers, oscillators, amplifiers, and in the memory chips like ROM and RAM. Therefore, I like to focus only on the physics of depletion region, the so-called region of such developments in the field of rectifier diodes, Zener diodes, photodiode, light emitting diode, solar cell, Schottky diode, laser diode, varactor diode, impact diode, sometimes we named as avalanche diode, and the tunnel diode, and uses of diodes in ROM and RAM memory, and finally in transistor, FET and MOS devices also. Thus, today's electronic industry is the assimilation of these devices, where the physics of depletion layer contributes the mother role to our goal. Now the questions about the depletion region are: what is depletion zone? How this zone formed? What are the parameters of this zone? The action of this zone, the uses of this zone, and finally our conclusion about the role of depletion zone. Before going into the detailed discussion of the depletion region or depletion zone, we must have some idea about different types of semiconducting material of the type of intrinsic and extrinsic semiconductor having N and P type, and their corresponding different energy levels, including the energy levels of Fermi energy and the important charge carrier like majority and minority carriers. Here we note that the doping of pentavalent atom like antimony that contributes its fifth electron as a free electron in the conduction band of the silicon lattice structure. Therefore, as per the doping density of this dopant atom, we get some excess electron, the negative charge in the conduction band of this total material, and hence we term the material as negative type or N-type semiconductor. Similarly, the doping of trivalent atom like boron that creates an excess hole in the valence band structure of the silicon lattice structure, and as per the doping density of this dopant atom, then we get number of excess holes in the valence band of the semiconducting material, and hence we term the material as a positive type or p-type material. Also, I also like to mention here that the antimony atom, the doping, and the boron atom gives the nature of some immobile ions. In the case of antimony, it behaves like a positive immobile donors, and boron behaves like an immobile negative ions. Now, in figure A, for intrinsic semiconductor, we note that the total number of holes and total number of free electrons in the conduction band are same, and this electron hole pair basically generates with some external heat energy, and they are termed as thermally generated free electrons. And because of the same number of free electrons and holes in such type of semiconductor, we get the hypothetical Fermi energy level just at the middle of this band gap. And in case of N-type semiconductor, that is extrinsic type semiconductor with the dopant of pentavalent atom like antimony, we get some excess free electron in the conduction band. As a result, the dopant atom, in that case the antimony atom, reacts with the like an positively charged immobile ions, and the Fermi level lies just below the conduction band. And in case of p-type semiconductor with the dopant atom like boron, we get some free holes in the valence band, and as a result the Fermi level lies just above the valence band energy level. About the concept of majority and minority carriers, here we note that for an n-type material with the dopant atom like antimony, phosphorus and arsenic, we get excess number of free electrons in the conduction band, and these electrons due to high number of free electrons in the conduction band compared to the holes, they are termed as majority carriers. Here note that when p and n-type material brought together, the electron and holes migrate across the junction to form the depletion layer and a potential difference. So, what is depletion region? That is the specific two regions at PN junction formed by immobile opposite charges resulting the depletion of mobile or free charge carriers is called the depletion region. Also note, any free charge carrier formed in this zone will be soon drifted by the field of depletion zone. Here we consider a schematic diagram of an unbiased asymmetrical PN junction. The asymmetry in that sense that we consider the doping of the p side is slightly higher than its n side counterpart, and as per my earlier discussion regarding the diffusion across the junction, we get some portion of the n side nearer the junction which becomes positively charged, and on the other hand the n side becomes negatively charged. Actually here, for example, all the arsenic dopant atom becomes positively charged and the boron dopant atom becomes negatively charged, and due to the interatomic electrostatic interaction between the two charges, we get an electric field and a potential difference. That is sometimes called is the contact potential difference, and the field and potential difference is of the such order that after some diffusion through this junction, further diffusion of any carriers through this junction naturally ceases, and the field and potential reacts like as a potential barrier for any further diffusion of electrons from n side to p side. And we note that in this region there exist no free electrons and holes. That is why it is termed as depletion region. And due to higher doping, the width of the depletion zone in the p side is lower compared to n side, and the total width of the depletion zone may be considered as the summation of xp and xl if we consider the metallurgical junction is at the origin of our coordinate system, and the remaining portion of this n side is neutral with its usual majority electrons and minority holes, and on the other hand the p side remains some majority holes with its minority electrons. Here we consider the Fermi energy level position for an unbiased PN junction diode. We note that in the neutral n region of the n-type material, there exist majority electrons, free electrons in the conduction band, and few holes, that is minority carriers, in the valence band of the n side. And similarly for p region, neutral p region, there exist majority holes in the valence band and minority electrons in the conduction band, and it implies that these free electrons require some energy to transfer from this side to that side for an conduction process, and the required energy is equal to the built-in potential energy of the depletion zone that we have to determine just now. Now I want to discuss the drift and diffusion current mechanism at thermal equilibrium through the depletion zone of an unbiased PN junction. Here we note that an application of thermal energy creates an electron-hole pair in the N side as well as in the P side. And in the N side we note that we get an excess free electron in the conduction band of the N side with an excess hole in the valence band that behaves like a minority carrier. And in the P side, similarly, we get an extra electron in the conduction band of the P side that behaves like the minority carrier, and the holes created in the valence band of the P region behaves as a majority carrier. Therefore, these holes and these electrons, the majority carriers of P and N side, may diffuse through this potential barrier, and the minority carriers, the holes in the N side as well as the minority carrier of electron in the P side, may drift by the electric field developed in the depletion region in the opposite direction. That's why at equilibrium we have to see that the sum of this drift current and diffusion current will counterbalance each other. Here we note that the diffusion current and drift current are equal and opposite to yield a zero current across the junction. As a result, we are not able to measure this junction voltage or contact potential by any voltmeter. Now, about the value of diffusion current for both electrons and holes, we know that the diffusion current is directly proportional to its concentration gradient dN by dx or dP dx. Here dN and dP are basically the proportionally constant and defined as the diffusion coefficient for electrons and holes. Now we consider the same concentration gradient profile along the same semiconducting material here, where we note that the both value of P and N increases along with the positive x direction, that is the dN by dx and dP dx both are positive in the both cases. And we know that in natural diffusion process the charged particle moves from high concentration zone to a lower one. That is, in that case of the electron flow, we have to get the flow of electron from high concentration zone to a lower concentration one. That is why electrons will move from this direction, negative direction of x, and we have to get a current, electron current in the positive x direction. But in case of hole, the flow of hole will be in the negative direction, as well as the current due to the hole motion will be also in the negative direction. That implies that in a same semiconducting material under the same gradient profile of electron and holes in general, the diffusion current for electron and hole will be in the opposite direction. That is why we have introduced a negative sign here for the hole current. Now, for further clarification of drift and diffusion current through this PN junction under zero bias condition, we may consider the following diagrams. Here we note that the holes, the majority carriers in the p-type region, and the electrons, the majority carrier in the n-type region, they may diffuse in opposite direction without any presence of electric field. That is why they does not require any electric field gradient. But in the case of drift motion, we note that the hole, the minority carrier in the n-type region, and the electron, the minority carrier in the p-type region, they drift in the opposite direction in presence of the electric field, junction electric field. But the sum of the drift current for electron, the sum of the drift current and diffusion current for electron will be zero, and similarly for hole also. That's why under zero bias condition and at thermal equilibrium, even at thermal equilibrium, we are unable to get any current across the PN type junction diode, and that's why we are unable to measure the contact potential difference by any voltmeter that I have discussed earlier. Now, regarding the values of majority and minority carriers in the neutral region of the N side and neutral region of the P side of the PN junction, we observe that the majority hole density that exists in the valence band of the P side material, that is generated by P at the P side, the hole in the P side, that is approximately equal to the accepted doping density, and the free electron, that is the minority carriers in the P side, that is denoted by NP, number of electrons in the P side, is approximately equal to Ni square by Na, where Ni is the intrinsic carrier candidate density and Na is the accepted doping density. And similarly, in the N side, we see that the holes, that is the minority carrier that exist in the valence band, that is denoted by P in the N side, is also approximately equal to Ni square by Nd, and the electrons, the free electrons, the majority carrier in the N side that exist in the conduction band, that is approximately equal to Nd, the donor doping density. And we also see that if we consider the Fermi level is just below the conduction band of the N side and just above the valence band, then we can approximately equal to the band gap energy is equal to the built-in potential energy, that is QVB, that is, and where the built-in potential we have to calculate now, that is approximately equal to KT by Q. K is the ball band constant, is the temperature of the substance of the material, and N and D as we defined as the acceptor and donor density with its intrinsic carrier density. Therefore, the depletion region creates the following important parameters: immobile space charge region, a region of no free charge carriers, a static electric field, a contact potential difference, a depletion zone with a junction capacitance, and an uniform Fermi energy level throughout the semiconducting material of the PN junction under unbiased condition. In this diagram of the depletion region, considering the neutron region also, we have plotted the important parameters of space charge density distribution and electric field distribution and the potential distribution function inside the depletion zone of an abrupt asymmetrical PN junction, where the doping density in the P side is lower than its N side counterpart. Now in figure A, we have shown the distribution and it indicates that the width of the depletion zone in the P side is higher than the N side. And the doping density in the P side is lower than its N side doping density, but the area under this curve, that is the QNA multiplied by the width XA or XN, we get the value of this area like this: QA XPNA and equal to QA XNND, and where A is the cross sectional area of this PN junction diode. Now the total values of the negative charges is also equal to the total value of the positive charges in the depletion zone. And in figure B, we have shown the electric field distribution in the depletion zone, where this point indicates the maximum value of the electric field at the junction, and the field value linearly decreases with its distance along the depletion zone. At the end of this N side of the depletion zone, we get the zero electric field, and in the neutral region of the N side and as well as of the P side, we get the electric field value is equal to 0, and there exists no electric field, and that is the neutral side of both N and P region. And the value of the electric field may be calculated from the gradient of potential with its distance, and it may be calculated from the Poisson's equation that we have to discuss now. And in graph C, we have shown the potential distribution. Here we consider the potential at the end of the P side depletion zone is approximately equal to 0, and hence the positive potential at this end of the N side depletion zone that we have denoted by VBI, that is equal to the built-in potential, and the potential may be calculated from the electric distribution potential graph by integrating the electric field inside the depletion zone. Now, because of the high importance of the depletion zone field profile of the PN junction diode, we consider it again here, and it shows that if the electric field gradient in the both P and N side is directly proportional to the acceptor and donor density Nd, and if we consider the Na is greater than the Nd, the doping density at the N side, then we get the high field gradient in the P side with lower depletion region width compared to its N side depletion zone. And the area under this total graph of the considering the P side and N side, the area under this electric field profile gives the built-in potential VBI, as we have to calculate now from Poisson's equation, and the electric field value at any point in the N side or at any point in the P side may be calculated from this relation, that is electric field is a function of x, where xn is the depletion region end of the N side, and similarly for P side also, and putting the value of x, that is at the metallurgical junction of the PN junction diode, that is contact point, we get the maximum electric field E max, and that may be calculated putting the value of x here 0, both in N side and P side, we get the value of maximum electric field Q Nd Xn by, that is electric field also actually proportional to the Nd, the donor doping density as well as the acceptor doping density, and epsilon is the permittivity of the semiconducting material we have considered. So from Poisson's equation, we know that the potential at any point x in the depletion region is a function of space charge density rho x related by this relation. Here epsilon is the electrical permittivity of the semiconducting material. Therefore, the electric field at any point in the depletion region we may calculate from the gradient of potential by this relation, and the value of electric field at the neutral N region on P region equal to 0, that is when x is less than equal to minus xp, that is the end of the depletion region in the P side, as well as the above the depletion region of the N side, that is x greater than xn. And the contact potential difference can be found from the integral value of electric field inside the depletion region limiting from minus xp to xn, and that is defined as built-in potential or the contact potential. Now, it is also important that under equilibrium, the contact potential difference may be also calculated from the net zero current of dipped and diffusion processes, as I discussed earlier from these two relations. That is where the PAX is the minority carrier density, and this is the dipped component of current, and PXAR is the majority carrier concentration of the holes, and which is related to the diffusion component. And by the calculation from these two relations, we may calculate the value of built-in potential. Now, using Einstein's relation, that is the ratio of dP, which is mobility parameter related to holes, and the dP is the diffusion coefficient for majority holes, and mu p is related to the mobility parameter of minority holes, and the ratio is equal to kT by Q, where K is the Boltzmann constant and T is the ambient temperature of the material and Q is the electronic charge. And from the relation using electric field and potential, we get the expression like this, and we get from this the relation between potential and the hole charge density, and from this we get, now integrating the above equation and considering only the one type of charge carrier, that is the hole density throughout the depletion zone, and limiting from the value of Pp to Pn. That is, Pp is the majority hole density in the P side and Pn is the minority hole density in the N side. Limiting the value of potential as Vp and Vn at the above across the end of the depletion zone, we get the difference between P, Pn and Pp like this, integrating the values and defined as the built-in potential. Now considering the Pp approximately equal to the accepted doping density in the P side, that is the majority carrier density holes in the P side, and the minority carrier hole density in the N side. From the relation of law of mass action, we get the standard form of the potential value, built-in potential value, and from which we conclude that the built-in potential is directly related to the temperature of the substance as well as the doping density of the P side as well as the N side, and where Ni is basically a constant, the intrinsic carrier density at a particular temperature. Therefore, the contact potential difference or the built-in voltage inside the depletion zone may be plotted in this way, indicating the built-in potential difference that we have just calculated now, that basically depends on the value of doping density mainly. And now we have to show that this potential distribution may also be calculated from the width of the depletion regions. Here we again indicate the potential distribution function at any point inside the depletion zone. That is, we consider here the potential at the end of this P side depletion zone as a zero reference value, and the end of this N side of the depletion zone as phi n, where the potential at any point x in the P region, that is denoted by, that is any point P, you may consider x equal to this point, and that may be denoted by phi p, may be calculated from this expression, and at the edge, that is at x equal to xp, putting the value of x equal to xp, we get that phi p equal to 0, and similarly the potential at any point in the N region, that is at any point N region of the depletion zone, we get the value of phi n, denoted the phi n denoted by given by this expression, and putting the value of x equal to xn, that is at the end of the depletion region, we get the value of phi n, and which is equal to this value, and this value may be equated with the built-in potential that we have just told earlier. In this expression, we note that the built-in potential also depends, may be expressed in terms of xn and xp. So we may denote the built-in potential in terms of the depletion region width as well as the doping density. So finally, I have tabulated the main 4 parameters of the depletion layer under zero bias condition, that is the depletion layer width, built-in potential, maximum electric field at the junction, and the depletion layer capacitance. And from this relation, we note that all values of the depletion layer width as well as built-in potential, maximum electric field, and the junction capacitance basically depends on the ambient temperature of the semiconducting material or the junction and the doping density of the N side and P side. And the depletion layer capacitance is very important for microwave semiconducting devices. So finally, we may conclude that the above properties of depletion zone are the basics of all semiconducting devices.